we went through was the vocabulary for how we can actually talk about the coordinate plane. So the horizontal number line going through the middle, what do we call this? The horizontal one through the middle is the x-axis. The vertical one, Abby, what would we call that one? Y-axis. The y-axis. Excellent, nailed it. And what do we call that little point right in the middle where the two axes intersect? We call it the origin. And we always have coordinates to be able to refer to just a single point on the graph, and the origin is what we say is 0, 0. So this is kind of the starting point. Again, I always think of it as a little dude hanging out in the middle. We also can talk about these quadrants, the 4 sections that the number lines break the plane into, where we have quadrant 1 is up where everything is positive, and then we start going counterclockwise for whatever reason. So quadrant 2 is over here, quadrant 3, and quadrant 4. So, like I said, we've got some information that we can actually plot on the graph just by looking at a single pair of points. We always have a set of brackets around this pair of points. When we're looking at this refers to the x value and then the y value. And I like to think about how it's alphabetical. If you sing the alphabet, x comes before y, and so x is always the first number, y is always the second number. So if we're looking at the point 2, -4, let me zoom in here. What we have is an x value of 2, a y value of -4. So we need to find the spot where those two things can intersect each other. So we're looking at kind of bringing this one over to the side and this one down to where we have a singular point down here. Oops, sorry, at 2, -4. And because we were given a label for this point A, we're going to plot the point exactly where it should go, and then just somewhere near that, we're going to write a nice capital A. For 0, 5, if we ever have a 0 involved, it's going to lie on one of the actual axes. So it's either going to be on this bold line, or it's going to be on this bold line. We just really have to decide which one. Since our x value is 0, that means we don't have to go right or left from the origin. It's going to be in line here, so we just need to find where y is 5. So that would be point B. The other thing we can do is it's sometimes very important to be able to look at a point and figure out the values for it. So this is almost easier, especially if there's numbers involved, like on this graph. The x value in this case is -3, so that'll go first. And the y value is 2. Sometimes we'll get a point that falls halfway through the middle of the boxes. If it's ever partway through the middle, we're going to assume it's just 0.5. I won't ever, for something like this, make you estimate anything else. So for this one, we're thinking the x value is 5. That's pretty straightforward. But the y value is hitting halfway between 1 and 2, so that would give us 1.5. What do we think so far? Excellent. Moving on, we started to look at different information that we could get from a graph. So we have our slope, which talks about the steepness of a line. And we also have the intercepts, which we'll see is where it crosses the bold number lines in the middle. So when it comes to the slope, we kind of, just by looking at something, we can decide if it's going to be positive, negative, 0, or undefined. And who helps us do that? Slope man. So if slope man is walking uphill, it'll be positive. He's always walking from right to left. He can't ever turn backwards. If slope man is walking downhill, our slope, the number that we get will be negative. And then slope man is most useful for really thinking about 0 and undefined, because slope man just walking on a horizontal line, just going for a stroll, no elevation, is 0 slope. And especially it's useful for thinking about undefined, because slope man cannot walk up a vertical wall like that. So it just cannot happen. And instead of just saying like NA or doesn't exist or something, what we say is undefined. And a lot of times your calculator, if you were to calculate the rise and the run, this appears when we're dividing by 0. And actually I'll just write that in here too. Divide by 0. That's really bad. And so that's why it's undefined. Whereas when our slope itself is 0, the 0 is on the top of the fraction, and that's not actually a problem. So calculating the slope, what we're looking at is the rise over the run. where the rise is the number of boxes you have to go up or down. The run is the number of boxes you have to go side to side. And then don't forget to simplify the fraction. And then let's do that actually for both of these graphs down here. Let's figure out the rise and the run between A and B. So we always start at point A and go to point B. This way I don't know, it just gives us somewhere to go. So looking at this, for our rise and our run, the rise is the number of boxes we have to count up or down. So in order to get from the level that A is on to the level that B is on, we have to go up, so that'll be positive. And this graph isn't the best, at least mine's a little bit fuzzy, but we have to go up how many boxes? Remember that we're counting the actual boxes themselves and not the dots on the kind of like intersection points. So what we're looking at here is 4 boxes that we have to go up. So our rise is 4, positive direction. Our run is how many boxes we now have to go from that point over to get to B. And again, we're counting the boxes themselves. So 1, 2, 3, 4, 5, 6, 7, 8 boxes to get there. And if it's either a small graph or kind of jumbled, you can kind of just look at the X values that are associated with those 2 points. So we're looking at plus 8. Putting this together as a slope, we have 4 over 8. Can we simplify it? Certainly. What can we divide by? We can divide by 4 on both the top and bottom. This gives us a slope of 1 over 2, which what this means is for every nice point on the graph, if we go up 1 and over 2, we get back to another nice point. So here we can see there's all of these other good little points along the way. So that helps us with our slope. Same idea, just looking at this one. Do we expect that our slope should be positive, negative, 0, or undefined?
Negative.
Yeah, it should be negative. Slope man is definitely going way downhill. So we anticipate that our number at the end should be negative. So that's really helpful to see if we got it right. But we still have to calculate the rise and run. So the rise. The negative comes from the fact that our rise is going down towards our negative numbers. So that is 1, 2, 3, 4, 5, 6. So negative 6. What's our run in this case? Positive 2. So we're going 2 boxes to get over to B. So our slope is negative 6 over 2. So we see that the negative is there. That's good news. Can we simplify it? What should we simplify it to? Negative 3 over 1. Yeah, when it comes to slope, we typically keep the 1 here just to make it still have that fraction form to have a rise and a run. So if we had to draw something with the slope of negative 3, then we know that we're going down 3 over 1 to get to the next point on our line, just like we did here. So down 3 over 1 got us there, and again. Next up, the other stuff that we talked about on a graph in terms of the features of the graph was the x-intercept and the y-intercept. So this is where it crosses the x-axis or the y-axis. And you're really just looking at the graph, zooming in on mine at least, I know yours is kind of small, and just saying, okay, where does it cross? Sometimes it gets a little bit funky, but our x-intercept in this case, where it crosses the x-axis, that would be right here. And that's at 2. So we're just going to write 2. What would be our y-intercept on this one? Negative 1. Yeah, we're looking at, okay, here's our y-axis. It's going to cross right there. So that's at negative 1. In this next one, things are a little bit weird for our x and y intercepts. Which intercept is normal on this graph? Can we just see? Yeah, we can just see the x-intercept. It's where it crosses right there. The numbers are a little bit covered, but looking at, okay, every 2 boxes is 2, so then this would bring us to negative 4. And then the y-intercept, we can't see it on the graph. Does a y-intercept technically exist? Yeah, in this one, because we could technically like zoom out for this and think, okay, this y-axis would keep going, and this graph would keep going and eventually cross over here somewhere. So we know that it exists, we just don't exactly know what it is. So we're gonna say unknown. But we do know, would our y-intercept be positive or negative? Yeah, since we anticipate it to be down here somewhere, that would definitely be negative. So we're going to include that information as well. Technically, if you wanted to, you could figure out the slope and then keep going until you know that we would hit the y-axis, but I won't make you do that. Okay. Any questions on this first section here? Just all about these xy coordinate graphs. Okay, our next point then is taking an equation and doing whatever we need to do to graph it onto a grid. And so this is where your ruler comes in for sure. What we want to do is create a table with values of x that will fit on the graph. And so our values of x that will fit on the graph, what's our usual starting point, if possible? Yeah, we're going to start with 1, 0, and -1, if possible. We'll see in this graph down here that we won't really like that idea because we have a fraction involved. But for this one, we have just like a normal equation. We have a normal grid that goes up by 1 for every box. So we're just going to start with those values. So what we're thinking is, okay, 1, 0, and -1. And then what we're going to do is determine the y value that pairs with each x value. And how we do that is by taking each of these x values, putting it into the equation, and then solving for what y is equal to. You don't have to show your work. I'm going to show my steps for just one of these. So we'll go y equals -4 times 1 plus 6. And so just following BEDMAS with this section of the equation, what we have is y equals -4 plus 6. And so what's y equal to? It's equal to 2. And so this gives us just one singular point. So I know it's a little bit of work, but we want to see, okay, that fits on the graph. We want to make sure that we have, I'm going to make the rules that we have to have at least 3 points that fit on the graph. That way we can check that they do fall in a straight line and that we're on the right track. But it doesn't make you do too much work. So x value of 1, y value of 2 would go right there. So it definitely fits. And now we do the same thing with our other x values. So if we put 0 into our equation, then what we have is y equals -4 times 0, where that stuff just cancels out. And so what we get is just 6 as our answer. On the actual test tomorrow, I will give you a lot more space if you're wanting to show your steps here. You will have that availability. Just on the study guide, I wanted to save room for more important things. But this does fit on our graph, so 0, 6 would go right there. Just looking at this, what do we think is about to happen with -1? Yeah, if these are right, then our line looks something like this, and our -1 point should be somewhere up here. We're going to test it anyways, just because it's in front of us. When we put -1 into this equation, then what we get is +4 plus 6, which gives us 10. So as we anticipated, that doesn't fit on the graph. But because I said that we want to have 3 nice points on the graph, what value should I try next for x? Basically, if we were to think, okay, this is probably our line, hopefully, we don't want to test anything else in the negative values, but we could maybe try to see what happens at x equals 2. So if we put 2 into our equation, what we end up with is -8 plus 6, which gives us an overall value of -2. So that does fit. That's excellent. We go here, and it fit where we anticipated as well, which is really nice. So again, we're making sure that we have at least 3 points that will fit on the graph. And now we want to connect the points with a straight line with your ruler and extend it to the edges of the graph. I really like it when you extend the line so that the line goes through the points and all the way through the grid, and then you can put the little arrows outside of the graph itself. This shows that it goes on forever and ever in those directions. This next one, like I said, is a little bit trickier because we have a fraction. In this case, that dictates what we want to choose as our x values. So since we have 3 on the bottom, instead of using these 3 values, we're going to do 3, 0, and -3 instead. This way, these are values that when divided by 3, it'll make our equation not so bad. And then we'll see if we need any other points from there. My other recommendation also is to rewrite your equation. You'll see next year that this is like the most common way of writing a linear equation. Spoilers for next year, you'll learn about something called y equals mx plus b. Yay. We love this. And that's this formation of the line. That being said, when we're actually putting values into the equation, it's easiest if we consider that x is on the top of the fraction instead of beside it. So I usually like to rewrite it so that we have y equals 2x over 3 minus 1. This way, when we put our value into the equation, what we have is 2 times 3 for this first one, and we're following BEDMAS. So we would do the top of the fraction. 2 times 3 is 6. So we get 6 here, and then we're saying divided by 3, and we finish that fraction. So this is giving us 2 minus 1, which is just 1. Again, if you're more comfortable actually showing your steps, that's a great idea, just like we did over here, but for every point, but just to keep it kind of more condensed. That one definitely fits on the graph, so that's great. Choosing 0 is always a nice option. When we put 0 into this fraction, the entire thing just disappears. So what we get is just -1 as our answer. That also fits on the graph. We love that. And lastly, if we put -3 into this one, maybe I'll actually try to show my work over here. Then y equals 2 times -3 over 3 minus 1. There we go. Cleaning this up, we get -6 on the top. Cleaning this up even further, the fraction just turns into -2. And then we have the -1 trailing at the end, which brings us to -3 overall. No, it doesn't. What did I do wrong? No, it does. We're good. So we get -3. That's also on the graph, so we don't have to do anything extra. It's great when our starter points just work out well. And now we grab our ruler and we extend it. All right, any questions from the front here? Okay, flipping it over, what we're looking at is horizontal and vertical equations. These ones are going to be kind of the easiest ones to graph. They're always just a straight line, either up and down or side to side. And the thing about these is when you look at the equation itself, they only have one variable. So either x or y. So what we're looking at is it'll either say x equals a number, or it'll say y equals a number. And really, this is just an equation that tells us what that specific variable is at all points on the line. So for example, when it says x equals 4, this is kind of just instructions telling us that x is always equal to 4. Which means that we can find a bunch of points with an x value of 4, starting maybe with our x-intercept. That's a nice one for sure. And just any other points along this line where x is equal to 4. And this is clearly forming a straight vertical line. So this one here is x equals 4. Y equals -1, same idea. This means that every single point on the line has a y value of -1. So we find, okay, maybe starting with our y-intercept, that's a great place to start. Any other point along this line also has a y value of -1, so I'm just picking some random points here. And we're seeing that those are clearly forming a horizontal line. So this one here is that. Same idea, but this time we're given some graphs of lines and we need to write the equation. I don't usually put two graphs on the same grid, but here we are. So this vertical line right here, we want to think about what is always consistent on this line. And first of all, looking at the intercept is a great place to start. So our x-intercept is -3, but also every single point along this line is -3 for our x value. So our equation is x equals -3. That's that one right there. Same idea looking at our horizontal line right here. We want to see what is consistent for every single part of this line here. This one's a bit tricky because it's going through the halfway point between 3 and 4. So we're looking at 3.5 as our y-intercept, and that really is just our equation as well. Y equals 3.5 would be that graph right there. Okay. Next up, we got into the section where we start looking at some real graphs, where we're looking at some of this new vocabulary to talk about how we can talk about it. So what we started with is our dependent and independent variable. So our independent variable is the variable that you can change or control. Usually, if we ever are talking about time, that will be included as an independent variable. The dependent variable is what depends on the first one. So this is what we're kind of measuring or what we're looking at. Usually, like we've talked about height, we've talked about temperature, always typically depending on the time of something. Next up, we talked about linear and nonlinear. So a linear graph is a straight line when it's graphed. A nonlinear graph just means it won't be a straight line. It might look close to a straight line, but we also know that that means that it has a consistent rate of change. Next up, we talked about discrete and continuous. So discrete is a graph made of separate points. So you'll see this is just a bunch of little dots. Whereas continuous is a graph with a smooth line or a curve where all of the values are measured, or really all of the values make sense. So this will be a line. But this line has to make sense at every single point in between all the dots that exist. So if you were to zoom in and have like weird decimal values or something, it needs to make sense for the story that's being explained. Next up, we have interpolation and extrapolation. So these were the big words to think about estimating stuff. So if we have a graph and we're looking at 2 points, or if we're looking at a point between two things that we know, we call that interpolation. And I like to think about that as in between. Stuff that we already know. Or we also have the idea of extrapolation. And so that's when you're taking whatever graph you have and you're extending it a bit further to see what you're predicting to happen later on. And so that's where we're thinking extend the graph. And then the last little bit that we have here is what we went over yesterday. So this is linear patterns and really looking at writing linear equations. So a linear pattern is a sequence of numbers, usually representing a situation of some sort, but it could just be a sequence of numbers. The important thing is that they increase or decrease by the same amount between each. We're going to cross that out and just say step, I guess. Figure is more when we're just thinking about those little square drawings. But what we're thinking is just a bunch of numbers that are always increasing or decreasing by the same amount. The amount that they're increasing or decreasing is what we call the rate of change. When we're writing a linear equation, there's kind of a structure that we always follow. We have our dependent variable is equal to whatever starting value that we have for the situation, plus that rate of change that we talked about, times our independent variable. And for these equations, when I ask you to write one, I'll typically give you instructions of what variables to use. So I'll say use t to represent time or use h to represent the height of something. These variables are actually just used in the equation themselves. Those will stay as letters in the equation. What we're looking for is then numbers to represent the starting value and the rate of change. Is we need to figure out that specific information and fit it into the equation. But these will stay as whatever variables we're talking about. Later on, you'll see this as y and x quite a bit more often. But for now, we're kind of thinking of more situational things. So for example, another t-shirt situation, just to really nail home like one example that you've seen a couple of times to like remember the structure of the equation. So not the most exciting one. A school has decided to purchase t-shirts for their grad class. It's going to be $14.50 per shirt plus a one-time design fee of $75. So this fits a linear pattern because each shirt costs the same amount. We're not saying like if it's a blue shirt, it's $15, but if it's a red shirt, it's $12. I don't know. We're just saying our rate of change is plus $14.50 for every shirt. Our starting value is the one-time design fee. So this only gets charged once just to like design the logo of whatever's happening. So that's $75. In this case, our dependent variable would be the cost of the order. How much does it all cost? Depending on our independent variable is the number of t-shirts that are ordered. So usually I would give you some letters, but what we're going to say is the cost is equal to, so that's our dependent variable. Our starting value is 75. So we'll put that into our structure. Plus, our rate of change is $14.50. And then our independent variable is the number of t-shirts that get ordered. So let's use T as a good one there. Once we have our equation, we can use that to find out some more information without just extending the pattern 80 steps in a row in this case. And so what we're saying here is how much will it cost to order 80 t-shirts, which means what we're doing is we're solving for C if T is equal to 80. And so putting this information into our equation and then solving for whatever the thing is that we don't know. Oops, there we go. What we get is C equals 75 plus 1450. And instead of T, we're going to write 80. And then we just need to do the math to figure out what all this is. When we're doing the math, we're following BEDMAS. So we're doing this chunk first. So we have our 75 plus, that'll be 1,160 when you multiply that out. It's a lot of t-shirts. And then adding that together, finally, our total cost is 1,235, which we maybe just want to solve it like normal, and then on the side, write it with units. Because we're talking about money here. And our very last section here, thank you for bearing with me. Same idea, but this time instead of having like a real world problem, we're looking at this pattern that's represented by the number of squares based on the figure number that we have. So here we can see that we have 4 squares in figure 1, or 4 boxes. In figure 2, we have 7 boxes. In figure 3, how many boxes do we have? We have 10 boxes if we count all the ones that are shaded in. Which means, what is our common difference? What is it going up by every time? Just 3 boxes. Specifically, we're adding 3 boxes to the end of the column, essentially. So if we draw our next figure, we've got this weird little 1 at the top. And then we're looking at these stacks of 3, but we're just going to drop it down 1 more level. And so here, the number of boxes that we should have in this example is now 13 boxes. So clearly our rate of change is plus 3. Our starting value is not just kind of the first picture that we see, but just like what we saw up here, our starting value up here was how much we had to pay before we bought any t-shirts. So when T was equal to 0, which means our starting value for this one is when the figure is equal to 0. So we need to back our pattern up 1 step, which means instead of adding 3 boxes, we're destroying 3 boxes, and so all we have is 1 lonely little box left. And so our figure 0 is just 1. There we go. And then we're going to fit this into our structure of the equation again. This time our dependent variable is the number of little boxes that we have, or the number of squares. And so I'm going to put n for that. So that was our dependent variable, is n. Our starting value is just 1. And then plus our rate of change, which is 3. If we were getting smaller every time, it would be -3, but we're not. And then times our independent variable, which in this case, it depends on which figure we're looking at. So we're going to make that f. So kind of fitting all of that together, 1 plus 3f as our equation. If you're ever questioning your equation, what you can do is take some information from the pattern that's clearly in front of you and fit it in just to make sure that your equation works. So if we put 2 in for f and we have 7 for the number of boxes, if we look at the 2 halves of this equation, it does make sense. Because when we math it out, we get 7 on both sides. And so lastly, determine which figure will have exactly 145 squares. So what this is asking for is determine which figure. So we want to figure out what f is. Oops. And we're saying exactly 145 squares. And so that's the number of squares equaling 145. In this example, this is where the thing that we're solving for is trapped within the equation. So we're going to have to use inverse operations from Unit 5. So we get 145 is equal to 1 plus 3f. And we're going way back to just thinking, okay, we have our 2 sides of the equation. If we are solving for f, that means that we need to get rid of this 1 first to cancel it out. So we get 144 is equal to 3f. How do we get f by itself? Divide by 3, which means our final answer is 48 equals f. And so you might just want to write that out as like an actual answer of just figure 48. Because if there's ever like words or patterns or situations happening here, if you just give me a number, I'm like 48 what? Is that 48 boxes? Is that figure 48? What's going on? And so this just helps clarify that it's figure 48.